Let's try to get started. We've already talked a little bit about internal energy. It's the energy a system has when viewed from inside the system, when viewed from the center of mass reference frame. So an object as a whole is moving. The object possesses center of mass kinetic energy, may or may not possess internal energy. But once you observe from inside the moving object, you don't observe the center of mass motion, but you do observe internal energy changes. And we also mentioned the other day that this internal energy could have different categories. For example, you could have the translational component, a vibrational component, a rotational component, and you could have other components as well. For example, an electrostatic component, you could have, the system could be charged, the positive centers could be attracting the negative centers, the positive centers could be repelling one another. So there is an electrostatic contribution to the internal energy. There could be chemical energy. For example, energy stored inside the ATP molecule. There could be magnetic energy, and so on and so forth. अब प्लीज़ खामोशी से बैठ जाएं ताकि हम शुरू कर सकें. शुक्रिया. थैंक यू. Are we in a position to start now? So if you look at the translational, vibrational and rotational motions, these are motions of the components of the system. And if you take the random components of these motions, just take the random parts, you get a kind of energy that is called thermal energy. Why is there constant commotion at the back? So these components, the translational, vibrational and rotational components of the molecule, they can have an ordered part and they can have a disordered part. So the disordered part or the random part is given a name, and that name is thermal energy. Now, how do we measure this thermal energy? Suppose I draw this, my solid, my archetypical solid, which comprises these atoms that are bonded with one another through these spring-like interactions. I've drawn a two-dimensional pattern, but really it is three-dimensional, so I can have atoms at the back. So I can have atoms at the back. So this is a perspective view of the solid, and there are bondings between the atoms at the back and the ones at the front, and each of these bondings is represented by a modified harmonic oscillator Now all of these atoms are undergoing translational, rotational, vibrational, kinetic motions. For example, in the case of a solid, the equilibrium position of these atoms is fixed, so they are undergoing vibrational motion, right? They are vibrating. These springs, each of these springs is compressing and expanding, each one of them. And there could be an ordered compression. For example, all of the springs are being compressed at the same time, and all of them are being extended at the same time, which means if you have a solid and all of these springs are compressing and expanding at the same time, it's like the solid is breathing. See, it's dilating and compressing. So this is ordered motion. But there could also be a random component, that is, all of these springs, some one of them are undergoing compression, another one is undergoing expansion, and they are in different phases. For example, two of them could be compressing, but one could have gone further out, right? So there is random vibrational motion. This random vibrational motion comprises what is called thermal energy. Now, how do we measure this energy? That's the question. How do we measure E thermal? And remember one thing, this is microscopic motion. The solid as a whole, if you have this piece of chalk, it's at a certain temperature, which is the room temperature. You can't see it breathing, it's not moving, it's not expanding and dilating. But the atoms inside this chalk material, they are undergoing these random vibrational motions. The compressions and expansions are going hand in hand, and they are out of phase, right? So probably this spring is expanding, but it's at 3/4 of its amplitude. This spring is also expanding, it's at half of its amplitude. This spring is compressing, and so on. So there is random vibrational motion. This random vibrational motion gives rise to an energy which is called the thermal energy. Now, how do we measure this thermal energy? Now, ideally what we should do is we should be able to look at the kinetic and potential energy of each one of these harmonic oscillators, right? So every harmonic oscillator will have a kinetic and potential energy. That is what we discussed in the previous class. Now what we should really be able to do is to have a record of the energies of each one of these harmonic oscillators. Suppose we have a solid in which there are 10 raised to power 23 atoms, a very large number of atoms. You have 1 mole of a solid and there are 6 into 10 raised to power 23 atoms. Now, is it possible to actually find the energy of each one of the harmonic oscillators? No, it's not possible. And this is just the number of atoms. The number of connections, each atom is connected to 6 neighboring atoms. So the number of harmonic oscillators per atom is in fact 6. So you really have to find these many values of the energy. But that's not possible. So how do we measure thermal energy? How do we measure this random motion? So one way of measuring this random motion is to use some kind of device. So what a theorist would do is he would write the energy of each harmonic oscillator inside this solid and sum up over all of these energies, and you will get the thermal energy. But we know that this is not possible. It looks good on paper, but it can't be done. So let's try using some device which actually measures this thermal energy. Suppose I have this solid. I make a small hole inside the solid And inside this solid I place a glass bulb thermometer. So this is a mercury thermometer. And this object is insulated from its environment. So this is some kind of insulation, thermal insulation. Now when I place this glass bulb inside the solid, the mercury level would rise or contract depending upon what the temperature of the solid is. So what really is happening here is that there is thermal energy inside this solid and there are atoms everywhere in the solid, correct? And those atoms are undergoing random motions. Alright? When you make contact with the thermometer, with the glass of the thermometer, there is glass and then there is mercury inside. So the walls of the solid make contact with the glass, or if there is air intervening, if there is no physical contact between the thermometer, the molecules of the solid, the atoms of the solid make contact with the air molecules, right? And they transfer their energy to the air molecules. So they are vibrating in random directions and an air molecule sees these vibrating atoms and they pick up energy. That is, there is some kind of energy transfer to the air molecules. And now the air molecules are undergoing random motion. Remember, it's all random motion. Now the air molecules are striking the walls of the thermometer, the glass walls. They impart energy to the molecules of the glass. Now the glass is really a disordered solid as well. So the atoms inside the glass, they start undergoing random vibrations. It's like a domino effect. But the motions always remain random. There is no order to the motions. And then the glass imparts its random motion, its random energy to the mercury. And the molecules in the the atoms in the mercury, which is a liquid, they start undergoing random vibrational, random rotational and random translational motions. And as a result, there is energy transfer. There is some kind of energy transfer from this solid to the mercury. And this is transfer of random motion. One question: do the atoms of the solid do any work on the air molecules? Do they do any work on the air molecules? Work एक physics की term है. Yes or no?
Yes.
Yes, they do. So there is an individual solid atom. It's pushing an air molecule. So it is actually doing some work on the air molecule. However, there could be an air molecule, another air molecule that is pushing back on the solid. So the net direction of the overall force is zero. But each individual atom on a microscopic level is doing work on an air molecule. And an air molecule on a microscopic level is doing work on a glass molecule. And a glass molecule on a microscopic level is doing work on the mercury atoms. So yes, there is microscopic work, but no macroscopic work. ठीक है? So this energy transfer, which I denote by Q, this energy transfer Q entails microscopic work. but no macroscopic work. And there is eventually there is transfer of thermal energy to the atoms of mercury. Now the mercury column expands. Now why does the mercury column expand? We know its thermal energy is going up, so we must have an explanation of why the column is expanding. Correct? So let's look at the potential energy curve again. Or the potential energy curve, UR. Let's choose the Morse potential. Alright, so this is an equilibrium distance between two atoms. Suppose this is the Morse potential for mercury. Two mercury atoms come close to one another, they form this potential energy curve. Now at a particular value of internal energy or a particular value of thermal energy, we can represent the energy by a straight line. Correct? ये potential energy का curve है, इसके ऊपर एक straight line total energy को represent करेगी. So let's draw the line here. Before the thermometer was in contact with the solid at room temperature, this is the energy of the internal energy associated with two mercury atoms coming close to one another. ठीक है? अब देखो ये एनर्जी की वैल्यू है. इस एनर्जी के साथ what is the range of R's? Since everything is at equilibrium, this R naught must be at the center of these points. Now suppose the thermal energy of the mercury column increases because it has picked up energy from the glass atoms which have picked up energy from the air molecules. So this energy goes up, right? This energy must go up on the potential energy curve. ठीक है, thermal energy बढ़ रही है. जब ये thermal energy बढ़ेगी तो we can represent the new energy by a line that is raised with respect to the green line because the energy has gone up. Mobile phone छोड़ दें. The energy has gone up. Now when the energy has gone up, what is the average distance between the two atoms? Has it gone up? Has it remained the same? Or has it decreased? It has increased because now if you interpolate these points onto the distance curve, the average has moved to the right, which means the average distance between the atoms has gone up. If this solid were at a higher temperature, more thermal energy would have been transferred to the mercury and you would get another curve, another energy line which is further up, and the average distance between the atoms goes even higher. Now when the average distance between two atoms goes higher, and on average there is a large number of atoms and the average distance between them is between any two of them is going higher, the volume of mercury starts to increase because now there is more distance between two neighboring atoms. And that is why as the thermal energy goes up of the mercury, thermal energy goes up, the volume goes up. So this is how volume expansion takes place when the thermal energy goes up. ठीक है? और आप इसको इस पोटेंशियल से डिस्क्राइब कर सकते हैं. अब आप ये देखें कि ये जो पोजीशन है इस थर्मोमीटर में मर्करी के लेवल की, इफ दिस इज द न्यू पोजीशन ऑफ द मर्करी लेवल, this position is indicative. It indicates the thermal energy inside the mercury column. Correct? And it indicates the thermal energy inside the glass walls of the thermometer, which indicates the energy of the air molecules, the thermal energy of the air molecules, which indicates the thermal energy of the solid itself. Remember that if this device has to work, there has to be good contact between the solid and the molecule and the mercury, and the mercury must have a small mass as compared to the solid. So I can calibrate this scale. I can calibrate this scale in units of thermal energy. ठीक है, तो मैं एक ऐसा थर्मोमीटर बनाता हूं. थर्मोमीटर दरअसल क्या कर रहा है मेरा थर्मोमीटर, ग्लास बल्ब थर्मोमीटर, which is filled with some liquid, alcohol or mercury or water. This can actually be calibrated in terms of thermal energy. And thermal energy has units, every energy has units of joules. But conventionally we calibrate it in terms of temperature, which has units of kelvins. So there is a one-to-one correspondence between the thermal energy and the temperature. The temperature is one measure of the thermal energy. Right? Later we'll learn that temperature is associated with the disorder or the entropy. But for now, the temperature, there's a one-to-one correspondence between the temperature and the thermal energy. Now there are other ways of measuring the temperature. This is not the only way. For example, I could have the solid, and I make grooves inside the solid, right? And then I have a battery, an ammeter, and I place some resistor inside the solid, and I measure the voltage across the resistor. So depending upon the resistance of this resistor, the voltage will change. Suppose I have another resistor in series as well. So this resistance will change with the thermal energy of the atoms inside the solid, and this resistance change will be registered as a change in voltage. So this voltage is a measure of the thermal energy inside the solid, right? So the thermometer, the conventional thermometer, is one device for measuring the thermal energy. There could be other devices for measuring the thermal energy as well, and the thermal energy has a one-to-one correspondence with the temperature. Now let's talk a little bit about energy flows. Alright, summary. The temperature is a measure of the thermal energy, and the thermal energy comprises the random components of the internal energy. Alright. Now, what is meant by energy flow? Suppose I have two solids. Right. And everything is insulated from its environment, from its surroundings. This is insulation. This is what we call a hot object. Okay? And this is what we call a cold object. Now the hot object is lying somewhere separate, the cold object is lying somewhere separate. You make contact between the two and everything is placed inside a thermal insulation. What would you expect would happen? Speak up.
Energy will flow from the hot object.
Right. So it has to be some flow of energy. So there would be energy flow from the hot object to the cold object. Now this energy flow that I've depicted by a green arrow, does it involve any macroscopic work? No, it doesn't. It only involves microscopic work, because the atoms that are in the hot object, they are undergoing random motion, and by microscopic means they are transferring their random motion to the atoms in the cold object. So there is microscopic work, indeed there is, but there is no macroscopic work, because the cold object the center of mass of the cold object does not really move. So there is microscopic work involved in this energy transfer. So this kind of energy transfer, which only involves microscopic work, is generally denoted by a Q, as I've denoted over there. And this energy in transit, this Q, which is energy in transit, which is energy that is in motion, or energy that is being transferred. Don't use the word motion. Energy in transit is called loosely, from a physics perspective, heat. Now avoid using heat as a noun. There is no such thing as heat in an object. Whenever there is energy transfer which involves microscopic work at the microscopic scale, and no macroscopic work, do we say that heat is flowing from one object to another. For example, this sentence that friction produces heat is very misleading. This is a very misleading sentence, because this implies that heat is some kind of energy inside the object. No, that is thermal energy. Thermal energy is the random motion of atoms or molecules inside an object. And that thermal motion, that thermal energy can arise by the transfer of energy or through other means, which we will shortly see. That increase in thermal energy does not depend upon the flow of heat into the object alone. In these examples, we've seen that Q, or energy, flows into the object through microscopic work. That is, heat flows into the object and it increases the internal energy. But there are other means of increasing the internal energy. There could be macroscopic work that is done on the object. There could be electrical energy that is flowing into the system, and so on. So only the kind of energy that involves microscopic work and no macroscopic work is called the energy in transit and is denoted by Q. Let me give you another example. And now we are proceeding to the first law of thermodynamics. Suppose you have a reservoir of water. Suppose this is Mangla Jheel, right? Now there is some river flowing into Mangla. Which river is it? Jhelum. Right? There is Jhelum flowing into Mangla river, into the Mangla reservoir. Now there is a certain volume of water inside the reservoir. Now this flowing river brings in more volume to the reservoir. Is this flowing river doing any work? on the reservoir? Yes, it is. Because there are forces. There's a pressure gradient that is making this river to flow. It's flowing from the Himalayas. There's a pressure gradient. It's doing work. Right? It's losing its energy, which means that there's some work that it's doing. So it's bringing in work. It's doing work on the reservoir. And as a result, the volume of water inside Mangla goes up. However, it is very possible, well nigh possible, that you have certain a barrage or floodgates. You close these gates and the input of water from the river ceases. There is no input of water. There is no water going into the reservoir. Now there is no macroscopic work that is being done. And the volume, would the volume of Mangla remain the same?
No, there will be evaporation.
Right. There has to be evaporation or condensation. Evaporation would decrease the volume of water in Mangla, or there could be condensation. There could be clouds hovering above Mangla. Could be a very cold evening, and these clouds would descend on the reservoir and they would condense and they would increase the volume of the reservoir. So even though there is no macroscopic work that is being done on this lake, yet the volume can go up or down. And this is a local phenomenon, this condensation. So this is condensation by these inward pointing arrows. This is evaporation by these outward pointing arrows. These are rather local phenomena. Local or microscopic phenomena. ठीक है? और ये देखें कि generally you cannot control, it appears that you cannot control these phenomena, these microscopic phenomena, but in fact you can. You can really think of putting an impervious layer, some blanket on the reservoir, so that its volume does not change due to evaporation or condensation. So this kind of microscopic phenomenon can increase the volume. Now the analogy with our system is very clear. The volume of this reservoir represents the thermal energy or the internal energy, because the thermal energy is nothing but a component of the internal energy. So it represents either the thermal or the internal energy. Let's stick to the internal energy. The volume represents internal energy, and the volume can go up or down depending upon whether you do macroscopic work or microscopic work. The microscopic work is denoted by Q and the macroscopic work is denoted by W. So we have a relationship which is the change in the internal energy is due to the sum of microscopic work or energy that flows into or out of the system by virtue of microscopic work, which we generally call heat, plus the macroscopic work plus some other forms of energy, any other forms of energy transfer. And this statement, generally you don't write this in textbooks, but you really must have other forms of energy as well. This statement is called the first law of thermodynamics. G.
Sir, when floodgates are closed and the water hits the floodgates with very high pressure, would it affect the volume of the floodgates?
Of the floodgate, I do not know the exact construction of how floodgates are made, but there will be no water flowing into the reservoir, which is our system of interest.
But when
There will be excessive pressure. There will be pressure on the flood.
right,
There will be pressure, but there will be no transfer of momentum.
transfer of energy, but there will be transfer of energy, right?
There will be no transfer of energy because there is no work. Remember the work energy theorem. Only work can increase the energy for a microscopically moving object. So there will be pressure, but there will be no transfer of momentum or transfer of energy.
But what about the microscopic work?
There will be no microscopic work because there will be no transfer of Q between the river and the floodgates. Okay, let's talk about an example. Suppose I have a heater, right? An electric heater that we use in the winters. And suppose it is drawing 1 kilowatt of electrical energy. Right? Now what is a heater? The heater is simply a coil of resistive wire. बातें न करें, generally nichrome. It is connected to the power supply. There is current that flows through the nichrome wire. When the current flows through the nichrome wire, since this nichrome wire has resistance, there are collisions between the moving electrons and the atoms of this resistive wire, and the random motion of the atoms inside the nichrome wire increases, which means that the internal energy goes up, the thermal energy goes up. Right? Now suppose this heater is operating such that the temperature of this wire, the temperature of this resistive wire T, remains constant. Now, could you tell me, please, what is the value of Q and what does it mean? I give you 1 minute to think about it. I would like to know what is Q, what is the numerical value of Q, and what is its meaning? Think about it. करके दिखाओ, बोलो ना. सोचो. W क्या है यहाँ? माइक्रोस्कोपिक कौन सा वर्क हो रहा है यहाँ? मैक्रोस्कोपिक वर्क हो रहा है यहाँ? साइड एनर्जी वाला.
इलेक्ट्रिकल जो एनर्जी होती है IVD वो तो थर्मल एनर्जी में कन्वर्ट हो जाएगी.
ठीक है, लेकिन थर्मल एनर्जी कन्वर्ट होगी तो टेम्परेचर चेंज हो जाना चाहिए, तो नहीं हो रहा चेंज.
So because there is no temperature change, there is no transfer of energy.
There is no transfer of energy.
No, because the temperature doesn't. There may be, but not at the macroscopic level.
There is.
There is, but it will be both sides if the temperature
No.
is to remain constant.
Anyone is confident that he or she has an answer? All right, let me come over to you.
I think it's I square R. Since there is no other work done, the heat energy should be equal to the energy.
हीट एनर्जी का भी लफ्ज़ नहीं इस्तेमाल करना.
The thermal energy.
नहीं,
नहीं.
तकरीबन ठीक है लेकिन रीजनिंग गलत है.
Q would be 0 because
Speak up.
I square RT probably the energy dissipated
Which is,
in the resistance of the nitrogen.
so what is the value of Q? I square RT. What is its value? 0? You see, this is a very simple application of the first law of thermodynamics. The increase in, let's first decide what is the increase in the internal energy. The internal energy in this case can only increase. There is nothing that is doing macroscopic work, right? The nichrome heater is not being compressed or it's not moving and jostling around. There's nothing that is doing macroscopic work, right? So the internal energy changes because of thermal energy changes, but the temperature is constant. So what can we say about the internal energy change? 0. There is no change in internal energy because the temperature is constant, which means there is no change in thermal energy. So delta E internal is 0. But the second law of thermodynamics says that this is equal to Q, some energy transfer in the system. And this is microscopic, plus some macroscopic work that is done on the system. Is there any macroscopic work being done on the system? No. But there could be other forms of energy input. And here we have a case of electrical energy input, E electrical, and that is 1 kilowatt. Okay, we can also talk about per unit time as well, so let's multiply this with time with 1 second. So what is the value of W? 0. Right? G. Because the temperature remains constant. There is no change in temperature, which means there is no change in the internal energy. ठीक है? अच्छा, अब ये तो 0 हो गया. This means this has to be non-zero. So Q has to be equal to, if we talk about the energy transferred per unit time, this has to be equal to minus 1 kilowatt. So what this means, the numerical value of Q is minus 1 kilowatt, and what it means that all the electrical energy that is going in to the nichrome heater is being transferred out of the heater through microscopic work, but no macroscopic work. It's being transferred out of the heater through what we generally call heat energy. It's energy in transit. It's being transferred out of the heater, and this is available for us mortal human beings to heat ourselves. ये हमें available है, ये energy. This is heating up the room. So this is a direct, simple application of the first law of thermodynamics. ठीक है, समझ आ गई? जी.
Sir, you mentioned temperature is constant, but you're still saying that the heater 1 kilowatt is heating the room.
तो देखो ना, वो जो इलेक्ट्रिकल एनर्जी इनपुट हुई हीटर के अंदर, ठीक है, इट्स नॉट इंक्रीजिंग द टेम्परेचर, which means it's not increasing the internal energy of the atoms of the nichrome wire. Their average random motion is still the same. But where is all of the energy going? It's going out into the room. So this is very possible. If you have a household heater, baat sune gaur se, we have to connect physics with our daily lives. Physics is not just present in textbooks. if we have a time axis here and the temperature, बातें ना करें please, and the temperature of the nichrome wire, and you plug the heater into your mains outlet, the temperature starts from the room temperature, it generally goes up and then it tapers off. It reaches a steady value. So this question is dealing with a steady regime. If energy keeps on flowing, electrical energy keeps on flowing, and the internal energy keeps on increasing, you will eventually have a small sun in your room because the temperature is going rapidly up. But the temperature is stabilizing because there is energy transfer to the environment. As soon as the heater heats up, there is a large temperature gradient between the nichrome and the atmosphere. So the heat losses increase. The energy that goes out into the atmosphere also goes up. Of course, in this region, the thermal energy and the internal energy, they go up. But once you reach this steady temperature, the internal energy remains constant. Okay? So any questions up to so far? So now let's switch gears a little bit. We've dealt with the first law of thermodynamics. We're going to look at several examples in the tutorials and the recitations. Let's switch gears a little bit. And before we look at the second law of thermodynamics, let's talk about something else. But one question. Is this first law of thermodynamics have anything to do with the conservation of energy? Yes. It's simply the law of conservation of energy put forth in a different kind of language. I would now like to talk about the fact that internal energy is quantized. चलें अब खामोश हो जाएं प्लीज. अब ये हमारा क्वांटम मैकेनिक्स से पहला एनकाउंटर है. दिस इज आवर फर्स्ट एनकाउंटर विद क्वांटम मैकेनिक्स. But before I tell you that the internal energy is quantized and what is meant by quantization, I would like to introduce to you a particle. And that particle is called a photon. It was generally said that the 19th century belonged to the electron. ठीक है, इलेक्ट्रॉनिक्स में रेवोल्यूशन आया, इंफॉर्मेशन टेक्नोलॉजी में, सिलिकॉन इंडस्ट्री, ट्रांसिस्टर 1947 में जब पाकिस्तान बना उसके साथ ही ट्रांसिस्टर इन्वेंट हो गया. ठीक है, बार्डीन ने ट्रांसिस्टर का इन्वेंटर था. तो इलेक्ट्रॉनिक्स में रेवोल्यूशन आया और फिर आपने इलेक्ट्रॉन की प्रॉपर्टीज को समझना शुरू किया, उसको कंट्रोल करना शुरू किया. बातें ना करें प्लीज, बहुत डिस्टर्बेंस होता है. So the 20th century belonged to the electron. Now it is said that the 21st century belongs to the photon. अभी photon क्या चीज है? A photon is, before I tell you, let me ask you, what is your conception of a photon? Please raise hands. आप बताएं. A packet of energy. Good. A massless packet of energy. So if it is massless, then would a photon striking on an object, would it not cause the object to deflect? But then it must have some momentum. But you say it doesn't have mass. Anyone else? It It has mass because of its velocity. It does not have inertial mass. It just has relativistic mass, but not many people understand it at the present, so fine, no, don't worry. Anyone else? Its rest mass is 0, okay. Anyone else?
With a fixed amount of energy.
It has a fixed amount of energy, so if it collides with something else, its energy, would it change or not?
Transfer.
All of it?
It would not exist.
It would not exist
If all
if all of it got transferred. Good. Anyone else? So you do have a fair idea of what a photon is. But in the sake of democracy, so that everyone knows what a photon is, all of you are correct. A photon is, we'll talk about particles later, but a photon, take my word for it, it's a particle. Or a better word, a very nice word, in fact, it's a packet of energy. It's a packet of energy So there is a certain amount of energy that this packet contains, and this energy is determined by a frequency f, and the energy inside this packet is given by hf. So this is the energy of a packet of a packet, or the energy of a photon. And this packet is moving with the phenomenal speed of light. So the speed of a photon in vacuum, of course, it can change in other materials. So this is very important. In vacuum only is c. And it can only move in vacuum with this speed. And it's not possible to change the speed of a photon. Especially, you cannot make it, if you have two particles, see, you have one large particle sitting on the floor and one small particle colliding with this large particle. There's a collision. This small particle will come to rest and the large particle will slightly nudge in the forward direction. Or if this were a small particle of the same size of this particle, an elastic collision takes place, it transfers all of its energy, all of its momentum to this particle. The first particle comes to rest, the second particle moves on. Now the photons are constantly striking these walls. They're everywhere, these packets of energy, but they never come to rest. So a photon cannot be at rest, right? Which is another way of saying that the rest mass of the photon is really zero, right? ये कभी रुकता नहीं है. ये जब रुकता है तो कुचला जाता है, खत्म हो जाता है. ठीक है, लेकिन जब ये स्पीड से मूव करता है, c की स्पीड से मूव करता है, it does have some momentum, right? It does have some momentum, and the momentum of the photon is given by h over lambda hf over c. Right? This is the momentum of the photon. Okay? And what is the momentum in classical terms? It's mass times the speed. The speed. So you can think of as this momentum being equal to some mass times c. So this is the effective mass. So this is the effective momentum of this object. And the effective mass turns out to be hf over c squared. ठीक है? ये देखो ये momentum है photon का, but we know from classical physics that the momentum of any object is given by mass times its speed. So there is some kind of effective mass the photon has, right? And this, let's call this some m effective, is given by hf over c squared. It's called the relativistic mass of the photon, which means like any other object, alright. So if you have the earth is a large mass. Does it attract other objects? Yes, it does. And why does it attract other objects? Because they have mass, right? So if I throw this chalk in a straight line, it's going to effectively come back to the earth, because this chalk has some mass, and the earth has mass, and by gravitational attraction the chalk will be attracted to the back to the earth. Likewise, I have this laser. If I shine this laser light onto the wall, the photons are being emitted, but these photons do have mass. So eventually these photons, if this earth were heavy enough, and this frequency would be high enough that the effective mass of the photon is high enough, you will actually see this beam of light actually falling back to the earth. That's what happens near a black hole. A black hole is such a massive object that light falls back into the black hole very easily. It does not escape the black hole. So a photon has these strange properties. G.
Isn't the speed of light universal?
It is universal. In vacuum it isn't.
The speed of photon only in vacuum.
No, in materials it changes. The speed of light is different. That's called the refractive index. The speed of light does change in other materials. You see, you need to have a photon of sufficient mass, and because the attraction depends on the mass of the two objects. Now, the Earth's mass is fixed, but you can move to a neutron star which has a very large density, very large mass, or a black hole which has very large mass in a very small volume. Or you could move to photons with much higher frequencies, so that the mass of the photon becomes higher. So a photon is affected by gravity. In fact, that is how Romer in the 19th century determined the speed of light. Because light, when it moves, alright, let me give you an example, a neat example. There's a distant star, right? But stars don't really look like this. They look like this in nursery rhymes, but let me draw a more physical representation of a star. This is a star, and this is our Earth. The star is far away, so it looks smaller. This is our sun. Now when light from this star, we see the star. Of course we see stars. But when light from this star moves out of the star, which means photons are being emitted by the star, they enter our solar system, they come close to our sun. Now the sun has mass, the photons have mass, the relativistic mass. This beam of light is bent by the sun, and it reaches Lahore, and we see the sun and we see the star, but we don't see the star in its actual position. We see the star somewhere here. So the real position of the star is somewhere, whereas the apparent position of the star is somewhere totally different. Because now this sun is acting like a lens for the photons just because of the mass of the sun and the mass of the photons. This phenomenon is called gravitational lensing. And the entire theory of general relativity deals with phenomenon of this kind. So a photon has rest mass 0, but it does have relativistic mass. Now let me जी देखो ये लाइट की बीम बेंड हो रही है, ठीक है? तो जब आप इसको ऑब्जर्व करते हैं you can only extrapolate back to straight lines. So it appears to you that this light is coming from here. So the apparent position of stars is different from where they really are, because the photons are being bent. G. Right. We're going to talk about that when we deal with the quantization of energy. That's a very good question. देखो इन्होंने पूछा है कि where do photons come from?
They originate when light moves.
When light moves?
Yeah, because they don't have any inertial mass, so they go to have that.
No, but what generates photons? What produces photons?
Electromagnetic fields rotating, vibrating perpendicularly.
But that is light, that is photon. But what produces photons?
Energy, loss of energy from when electrons travel.
Right. So we're going to deal with the source of photons in the next lecture. Where do those photons come from? Because that will lead us to the quantization of internal energy. अब जरा तवज्जो से कुछ सब्र हौसला तहम्मुल कोई नहीं. We're dealing with some very really interesting stuff here. Now let me present to you two scenarios. First of all, does everyone know what the electromagnetic spectrum is? किन लोगों को electromagnetic spectrum का पता है? Okay. So if I say blue light, what does it mean? In terms of photons, what does it mean?
Photons have -5.
-5 what?
Order. Frequency of order in the show are -5.
Units.
Hertz. No, wait, the hertz.
-5 hertz तो बहुत छोटी frequency. It's a photon.
That all other particles of elements of that electromagnetic spectrum are absorbed in only blue particles.
But what is a blue photon? If you see blue light, this is blue, right? So photons that are entering our eye, and the retina and the optic nerve and the brain is processing those photons, they're seeing a blue color, right? But this sweater is maroon colored. So what's the difference between a photon that registers as a blue photon in the retina and a red photon? The frequencies are different. So a blue photon will have a certain frequency or a wavelength. देखो बातें ना करो यार प्लीज. अब मुझे फ्रीक्वेंसीज याद नहीं है. 10⁻14 हर्ट्ज के ऑर्डर में है विजिबल लाइट के लिए. वेवलेंथ्स याद है. ब्लू इज रफली 400 नैनोमीटर्स. Red is roughly 630 nanometers. Green is roughly 550 nanometers. And so on. What about white photons? There are no white photons. But if you have a large number of photons entering your eye and falling onto the retina, and those photons have different frequencies, of the correct numbers. There are blue photons, there are red photons, there are violet photons, green photons, correctly mixed in the right proportion, you will see white light. But there is no such thing as a white photon.
Maybe the retina fails to judge which color it is.
That is also possible. There could be different kinds of aberrations in the eye, but the eye has a certain sensitivity function. For example, we cannot detect infrared photons, but the camera in the mobile phone can detect infrared photons. Certain animals inside the marine environment, like eels, octopuses, they can detect infrared photons. The blind dolphins in the Indus River, they are blind. They can't detect visible photons, but they can detect photons in the radio frequency regime. Right? There are insects that can detect ultraviolet photons. In fact, the eye is a very sensitive device. Appreciate this. Only 30 or 40 photons are enough to register a signal. यार बातें ना करो, क्या हो गया? The eye is an extremely sensitive device. Only a few photons are required to register a signal. But photons come in different frequencies. And I think all of you should know what the electromagnetic spectrum is. The visible range in the electromagnetic spectrum is very small, in fact. Here you have the red part, here you have the blue part. And this is increasing frequency. Let me use another color. So this is the axis of increasing frequency. So the visible range of frequencies is actually very small, and due to biological evolution, the human eye is a detector that can only detect in the visible regime. It cannot detect in other regimes. For example, your mobile phone signal, that also comprises photons, but our eye cannot detect those electromagnetic waves, those photons, and the eye cannot be used as a mobile phone. The eye is only accustomed to be used in a very narrow optical regime called the visible regime. ठीक है? और इसके आगे higher frequencies पे और तरह की light है. But all of them are photons, and they only differ in their frequencies, nothing else. All of them are moving with the same speed. So here you have the ultraviolet regime. With higher frequencies. Then you have the X-ray regime. Here you have soft X-rays. Then you have hard X-rays. Then even higher frequencies, you have gamma rays. Gamma rays. So all of these kinds of light, they are essentially the same. All of them comprise photons, and they differ in nothing but the frequency. But remember one thing, we've dealt with the photon as being a particle. But how can we define the frequency of a particle? This is something we'll deal with later. Right? On the other side of the spectrum, lower frequencies, we have the infrared regime. This is called the near infrared. This is called the far infrared. Then we have microwaves. So there are microwave photons with a certain frequency. And then we have radio waves. All telecommunication takes place somewhere here, around 1550 nanometers. This is the range between 400 and 800 nanometers, and so on. So this is the entire electromagnetic spectrum. So in the next lecture, what we're going to deal with is how these photons are generated. Where do they come from? They come from quantized internal energy levels. See you on Thursday, and there's going to be a demonstration, inshallah, on Thursday in the classroom. So be punctual, be there on time. We don't have much time for the class next